All right, welcome back, class. In our last session, we got a taste of the amazing world of compliant mechanisms. Today, we're going to roll up our sleeves and really start building our designer's toolkit. We'll do that by reviewing the core mechanics of materials that, make all of these incredible devices actually work.
So here's our game plan for today. We've got 4 key stops. We'll start by making sure we're all speaking the same language, the language of flexibility. Then we're going to break down the cantilever beam, which is really the fundamental building block for so many of these designs. After that, we have to talk about the limits of our simple theories. And finally, we'll get into the fun part, how to choose the absolute best materials to get the job done.
Okay, first things first. To even have a conversation about designing these things, we've got to be on the same page. And that common language is all about stress and strain. These two concepts are really the bedrock that dictates how any material is going to bend, stretch, and perform under a load. Now this graph, this is the foundation for everything we're going to talk about. It's absolutely fundamental. So on the vertical axis, you've got stress. That's the internal force the material is feeling. And across the bottom, on the horizontal axis, is strain. That's how much it's actually deforming. That initial straight line, that's our elastic region. The slope of that line is what we call Young's modulus, or E. And it's basically a measure of stiffness. The steeper that slope, the stiffer the material. But here's the critical part. See where that curve starts to bend and doesn't go back? That point is the yield strength, or SY. For us, that is our primary design limit. It's the do not cross line. If you push a material past that point, it stays bent. It's permanently deformed. So any good compliant mechanism has to live its entire life below this limit.
Okay, so let's take these ideas of stress and strain and apply them to the most essential piece in our toolkit, the simple cantilever beam. If you can really understand how this one little piece works, you're well on your way to understanding the whole puzzle.
Now, the equations on this slide, they hold a really important secret, a real designer's insight. Take a look at the deflection formula. Notice how both the length L and the thickness H are cubed? That's huge. It means geometry is by far our most powerful tool for design. If you double the length of the beam, you get 8 times the deflection. If you cut the thickness in half, you also get 8 times the deflection. It's this exponential relationship that lets us fine-tune our mechanisms to get the exact amount of flexibility we want. It's incredibly powerful.
So this linear theory is fantastic for building our intuition, right? But it's got a major flaw, a big one. It really only works for very, very small deflections. And as we know, the whole point of compliant mechanisms is to get large, intentional deflections. So we have to know where this simple model where it breaks down.
And here's the difference in a nutshell. Linear theory makes 2 big assumptions, that the beam's stiffness stays constant and that its tip moves straight down. But in the real world, when you have large deflections, the stiffness actually changes as the beam bends. It's a phenomenon we call stress stiffening, where it gets harder to bend it the more you bend it. And the tip doesn't go straight down. It follows a curved path.
This picture illustrates the consequence perfectly. That dotted line, that's what our simple linear theory predicts. It thinks the beam tip is going to end up way down there. But the solid line shows what really happens. You can see there's a big difference. For our compliant mechanisms, where large deflections are the entire goal, if we ignore these nonlinear effects, we're going to have massive errors in our predictions for both motion and forces.
So, this brings us to a really crucial question. How in the world do we pick the right material? How do we choose one that lets us get the largest possible flex without permanently breaking or bending it? This is honestly one of the most important choices a designer has to make.
This is the million-dollar question for anyone designing a compliant mechanism. Now, your first instinct might be to just pick the strongest material you can find, something like steel. But, as we're about to find out, the answer is actually really surprising. We can actually figure this out by just combining the equations we've already seen. So stick with me here. First, we define our failure point as the moment the max stress in the beam hits the yield strength, Sy. Then, we can rearrange that equation to solve for the maximum force the beam can take. Next, we just plug that max force right back into our original deflection equation. And after a bit of algebra, voila, we get this incredibly powerful final equation. Now look closely. The maximum deflection depends on 2 separate things: a geometry term, which is all about length and thickness, and a material properties term, which is this fantastic ratio of yield strength to Young's modulus, Sy/E.
And when we apply this metric to real materials, we get a huge surprise. I mean, just look at this table. High-strength steel has a monster yield strength, right?
but it also has a monster Young's modulus, a huge stiffness. So its performance ratio is about 5. Now look all the way down at polypropylene. Its strength is tiny compared to steel, but its stiffness is also incredibly low. And the result? Its sigma over E ratio is almost 25. That's 5 times better than high-strength steel for this specific job. This right here is why you see so many things with large, flexible hinges, like the clasps on a backpack or the lid on your shampoo bottle, made out of plastic. It's just better for the job.
But of course, in the real world, it's never quite that simple, is it? The SIMBI over E ratio is a fantastic starting point, an amazing guide, but a truly robust design has to consider other things too. Will the material slowly sag over time under a constant load? We call that creep. How many times can it bend back and forth before it breaks from fatigue? Is it sensitive to temperature or humidity? And maybe most importantly, can we actually make the part? And can we afford to? Good engineering is always about balancing all these different factors.
Okay, so let's just quickly recap the 3 essential tools we've put in our toolkit today. First, we've got to master the fundamentals. Stress and strain are non-negotiable. Second, we've learned how to use geometry and that super powerful sigma over E ratio to really tune a mechanism's performance. And third, we now have that ratio as our North Star, our guiding light for picking the best materials for high deflection jobs.
And that kind of leaves us on a cliffhanger. We know we need to use nonlinear analysis for these things to be accurate, but we also know that math can get really complicated really fast. So the question is, how can we simplify the modeling of these large deflections without getting totally lost in the weeds? Well, in our next session, we're going to introduce a really clever and powerful tool to do just that, the pseudo-rigid body model. I'll see you then.